Okay, so the radius of a nucleus can be determined from high-energy electron diffraction experiments. Explain why it is important that the electrons in the beam have the same kinetic energy. Alright, so if we're looking at this, what's actually happening then is we've got I'm just going to draw the nuclei here in a lattice, or actually just in a row. And if I fire, now these are all obviously going to be positively charged because they're nuclei. And if I fire a negatively charged electron at them, here's my negatively charged electron. Now, this is going to be fired through, and it starts off, and what it's actually going to be is attracted towards the nucleus. So, if I fired it faster, the time it would be experiencing that force would be smaller, so there'd be a smaller impulse, so therefore there'd be a smaller change in direction. So the first thing we're worried about here then, in terms of why the velocity is important, is the electrostatic scattering, i.e. the electrons being attracted to the nucleus. And that depends on the speed of the electrons, i.e. generally electrons travelling slower are deflected more. And they're deflected more because they experience the force for a greater period of time. Now, obviously, your kinetic energy is a half mv squared. So, if your velocity is affected by your velocity, it's the same as saying it's affected by your kinetic energy. So that's our first bit. Now, our second bit, again then, is these nuclei act as a diffraction grating. So, in this case, we're considering kind of the particle features of the electron, the electrostatic gravity. In this case, we're going to be giving the wave features of that electron. So, nuclei act as diffraction grating to the, and I'll put here wave-like electrons. Now, if we go back to our diffraction grating, what we've got is that d sine theta is n lambda. So the diffraction pattern that we get depends upon this, the wavelength. We also know from the de Broglie, or Broglie, but I prefer to say Broglie equation, that our wavelength of these electrons is h upon the momentum, which is h upon mv. So therefore, if we substitute in, what we've got is that d sine theta is equal to nh upon mv. So we can see again, this diffraction pattern is going to be dependent upon the velocity. So our diffraction pattern on the velocity of the electrons therefore, so if it's going to depend upon it, if our pattern's going to depend upon it, therefore what we want is to get a clear pattern, therefore we want uniform velocity. And so we can see two reasons. The first one, because the electrostatic scattering, and the second one, because of the diffraction, we want uniform velocity. So we know kinetic energy is a half mv squared, therefore uniform velocity means we want uniform kinetic energy. Hopefully that makes sense. Thank you very much.